Okay. Okay, everything should be better now. Welcome to Shelter Baikonur, where Marius will now tell us something about software-defined radio and how you can do really cool stuff without soldering anything. Give him a warm round of applause, that would be nice.
Everybody able to understand me properly? Zero? Alright, so now the acoustic level is okay. In the following, I'm going to talk about stuff you don't see every day, which characterizes wireless telecommunication in general, and what you can do with software-defined radio approaches that are currently out. I think at first I'm going to start with the wireless, or with the public speaking protocol. That is relatively easy. I think I reserve the left hand for people who cannot understand me, so I'm not accustomed to the acoustics here, and I don't necessarily know how it echoes in the power areas. So if you want to have better articulation, use your left hand, weave it, and I think I can adapt. For the right hand, that's an immediate question, and both hands keyboard. So start with a short disclaimer. I'm here in private, and I do not represent anybody else but me, which is necessary to point out for some people. And in short, I have an agenda which is mainly oriented in software design, so I'm not going to talk too much about the hardware or the design of a peripheral. So I have a focus here which I said and which is not realizable. But practically I'm going to talk about Python and C++ and not too much about the soldering action, which may be related if you design your own peripheral or your own daughter boards for USB. I'm going to talk about different use cases that apply for software-defined radio and how digital signal processing in general is realized. So first introduction, I'm Marius and I'm a software developer, so I'm not the hardware guy. I do some embedded software development, so I have something to do with hardware. I also do some industrial automation stuff, well, as you can see. My motivation here to dive into wireless is a set of omnipresence that we all, I think, have realized in this camp, since we wear badges, and I think everybody in here has at least one wireless device, therefore. I think everybody here can agree if we say that in this room there are more than 1,000 wireless devices summed up. So I think it is necessary to look at how these wireless devices work, because it can sum up to something like SmartNet, because it's omnipresent and we see it, but we don't necessarily know how it works in detail. And yes, software-defined radio in short is a peripheral that is shown in the red area. That's a flexible radio peripheral that these days mainly is realized with an FPGA that is bundled with an ADC. Maybe you have a signal processor and a DAC in the transmission path, and everything else is sent to your PC, which is shown there. So in short, you don't necessarily have to do that much soldering anymore, which is the approach behind that. The origins of software-defined radio are, well, as most stuff, or as some stuff in digital signal processing that is interesting, in military and classified research in 1984. And, well, the approaches back then were kind of huge and had a lot of resources, which are generally unavailable to us. But since a couple of years, there are cheaper radio peripherals, since developments in FPGAs increase. Software-defined radio is expected to be the dominant technology in radio telecommunications in the future by the Wireless Innovation Forums. And yeah, it's getting more affordable. There are some older peripherals that use sound cards as ADCs, but newer approaches, which are the approaches I'm going to focus, use FPGAs. In general, the use cases for software-defined radio are mainly commercial wireless, which characterizes mostly everything we use here, like DCT, GPS, GSM, Tetra, wireless LAN, and RFID stuff, and also custom protocols and stuff like ZigBee, which is 802.15.4. So you can verify specific requirements you're trying to realize with these protocols that may be real-time requirements, as an example. Other stuff is spectrum sensing and interference studies, which I'm going to talk about in the later slide. That is reliable communication design, which is stuff that was mostly possible in theory, which we can now realize. Of course, as I mentioned, the software-defined radio approach was born in the military, and therefore active passive radar stuff and in general stuff from security research and public safety is present, like SIGINT and COMET stuff, or field smart radios, which in general characterize technology which shall not be detected when it communicates. So you send signals and you cannot find out where they come from, where they origin from, or which are not detectable at all. In development, which can be very helpful but doesn't sound too interesting at first, is multi-megabit OFDM stuff, which you see mentioned in the later others. That is in general interesting if you do interference simulations, for example, but of course also for transmission scheme design. And also SDRs are used in radio astronomy, telemetry, medical imaging, wildlife tracking, structural analysis. So in short, it's a relatively dominant technology, which I'm going to focus, that has evolved to really kind of help define research in dimension fields. So GNU Radio is software that is used to control USRPs, for example, but there are other devices which you can use with GNU Radio. So it is possible to design your own peripheral that interacts with this open source framework. And it is used to develop transmission schemes. So you, in general, define a set of, you define your code with your parameters and all the necessary classes to demodulate and to modulate and to design a complete transmission or receive path. And you will be able to get the data with just that device. So it is adaptable to many transmission schemes. And GNU Radio has many algorithms included that can be, as I mentioned, modulations, filters, and in general stuff you have in the IEEE standards, for example. And GNU Radio, which I'm going to focus, has an interesting architecture, and it uses a language interoperability approach that interoperates C++ and Python with interface generator named Swig. And these days it has a graphical component, which is the GNU Radio companion that introduces XML for persisting parameters and connections. And you have some Python code again included in the GNU Radio companion. So in short, it abstracts hardware interaction with the radio peripheral, which can be whatever peripheral you prefer or which you want to build. It isn't necessarily limited to USRPs. And since I'm going to focus wireless communication in the following, I've marked out the stuff in the ISM band, which you see marked in this arrow that is orange. It wasn't supposed to be orange, but it is. And you see that there is wireless LAN, there is Zigbee, and there is Bluetooth, and they all walk in the same spectrum. So we can actually see that there might be some interference since Bluetooth has adaptive frequency changes. And wireless LAN covers, I think, the whole ISM band at some standards. Other stuff that is not necessarily ISM band is mentioned there as RFID or GSM, UMTS stuff, or your favorite stereo headphones, which practically can all be received with a USRP if you have the adequate hardware or the adequate daughter board. So I'd like to make sure that we all speak the same terminology. So if I speak about sample rate, I mean samples per second. So in a real-time system, the samples mark an amount of time that varies across what kind of sample rate I have defined. And if I speak about gain, I speak about a constant for the PGA. I'm not speaking about the physical gain, which normally refers to an electronic field. I'm speaking about the software side of things here in the following. Modulations have an extra section. We're going to talk about that. The wave for me is a moving curve. I think that there are various definitions about waves, but here is this moving curve. Pulse is a positive short amplitude. It's just going up like a wave. And a carrier is a mother wave. It's the wave that is modulated upon. And what you furthermore see is that I speak about the IF band, which is the inner frequency band, and the RF band, which is received at the daughter board. Normally daughter boards, at least at the USRP, downscale to the ADC frequency. And an ADC, DAC is an analog digital converter and a digital analog converter. So what you see at the picture is actually an amplitude, which you see as positive and negative values. And you see that there is omnivariant noise, which is characterized that the blue lines never approach or never are near to zero. They just don't hit zero. You see that the samples are actually increasing. That's what I mentioned, the sample rate. Yes, I tried this now. So what you're going to hear the following is the exact curve that is mentioned there, but it is sampled with 33 kilohertz and 8 bits per second. So it's simply, I'm going to mention this as PSK, which is phase shift keyring. That is a modulation system or a modulation algorithm that is used in IEEE 802.15.4, which is better known as ZigBee. I'll try to start this. Not too interesting, however. I tried. What you should have been able to hear is that there is always some sound which is characterized as noise, and that there are some louder parts which are the transmissions. So each positive amplitude here, or each of the larger squares define transmission. Trying to at least schematically explain what kind of hardware is working here or which hardware is standing here. At the USRP, you have a set of ports. You see two ports for the USRP2 above and two ports down. So in short, it has 4 ports. And you can have 2 different daughter boards because it has full duplex USB 2. And the daughter board is shown in the background for the black one, which is the USRP1. You see SMA cables, a signal processor, an FPGA in the middle, which is the large chip. And that is the hardware which is practically powering the USRP1. For USRP2, which is the newer variant, you see that it has only 2 channels. So yeah, there is one daughter board added, but you have just one daughter board or 2 daughter boards using float sampling and not complex baseband sampling. And the USRP2 has a more capable ADC, which is operating at 100 megahertz instead of the USRP1 that is something like 64 megahertz. And yeah, it has gigabit Ethernet, so it doesn't downscale to USB anymore, which characterizes the differences between these 2 devices that are mainly used to work with GNU Radio. So in short, how this works, you have an antenna at the USRP that is at the SMA port. And that antenna is normally used to receive the microwatt range depending on what kind of spectrum you're targeting. And it is actually montaged at the RF amplifier that boosts to the ADC input voltage. And some models, I don't think USRPs have this too much, but some models have a bandpass filter here that you can use undersampling and stuff. But at the daughter board itself, there is an analog frequency translation. That means you cannot use each daughter board for every frequency that you might have in mind. And the approach that is used is an analog mixer or local oscillator at the daughter board. The alternative is direct baseband signal acquisition, but that can only be used for stuff that is not more than 50 megahertz without aliasing, of course. So the daughter boards at the USRPs downscale to an intermediate frequency. And at the receiver system, you can have a set of filters. We can have a low-pass filter that only passes the first window, which you see here.
from 0 to a half F, and that means everything else is rejected. So that's practically a low-pass filter here. A bandpass filter is shown in the other picture that is only selective, so you can select your window that you are receiving or that you are passing. And in general, these filter systems, if they are in front of an ADC, improve the signal-to-noise ratio and save dynamic ADC range. All right, so what is actually working with the mentioned FPGA and the mentioned ADCs? We have, in a USRP, we have the FPGA and the ADCs interoperating with each other. And that is pretty much the approach which there is. It's a relatively simple approach. And the FPGA allows us to do real-time DSP, which is due to vendor DSP initiatives. Not too many vendors that don't have these initiatives these days. And that means we have a dedicated set of hardware multipliers in these FPGAs. And yeah, there are I/O pins. DSP is an I/O-intensive task. And therefore, there are gigabit serial transceivers, BGAs, and flip chip packages. And an FPGA uses less power than your normal CPU that you have at your laptop or so. So it keeps the power and the heat down, and it's a relatively low voltage system. So in short, we have an ADC, a DAC, an FPGA, and your PC, which now has to do the buffer for vectors that you're receiving from the ADC, the visualization, and all the digital signal processing algorithms. So the FPGA can do parallel processing, and it has fast signal path, and it has, or it should have, many hardware multiplicators. So that means we do more in software, so therefore we need more PC hardware. And yeah, we have a real-time system. That means actually if we are visualizing the signal that is current or that we now receive, that system needs to have adequate speed. So if we want to design a stack or something that receives signals with a USRP, we start, of course, with the software side of things, which currently has many open source start points. Your code can be test-driven, which is not necessarily true if you have the normal or the approach to use hardware, which cannot necessarily be tested at the creation or the design level in that depth. And then we have PC, which for USRP2, which I'm focusing here, handles up to 25 megasamples with IQ sampling. I'm going to talk about this in a later slide. So it practically works above 20 million 32-bit values per second. 50 million, which is 2 times 25 since it is complex baseband sampling. And we have a DDC, which actually downscales the received stream of vectors to something the port, which we have attached, which the peripheral is attached to, can process. The FPGA handles interpolation, and the daughter board downscales to IF and upscales to RF. It's a modular approach, and it's a relatively open design, so you can create your own daughter boards if you're interested in that. The schematics are open enough so that you can do this. And with radio, or in general with software-defined radio approaches, you always work with discrete values. So you capture the analog signal at the antenna, put it into an AF receiver, to an ADC, and actually then it comes to your code, and the code processes it to data that you can read or that you can represent. It can also be statistics or something. Doesn't necessarily need to be a transmission scheme for data. At the send path, which you see under the receive path, we see that the code is actually controlling the DAC and the RF transmitter, and then it is passed to an antenna. So in short, the code is as near to the antenna as possible, which is the approach for software-defined radio, not that there is too much abstraction in between. And this is used in many projects, which we can check out at CGRAN, which is a repository for available stacks for GNU Radio. And these stacks contain examples to use DECT, RFID, or Wi-Fi stuff. We have FM stuff. We have something which is MPOFR in IP, which is something for astronautics. So there is also experimental stuff. And it is relatively interesting to check out if you're interested in the details on how to realize digital signal processing with software-defined radio approaches. But all these stacks also define a sniffer. So I have mentioned that we have senders and receivers. Not every stack that is mentioned here has a sending path implemented, but practically receiving DECT with the USRP is possible, or Bluetooth, or Wi-Fi, or GSM, Tetra, whatever. The algorithms aren't necessarily in the graphical components of the radio yet. So yeah, due to the design of using an ADC with an FPGA, we can actually expose our code near enough to software so that we can realize that general purpose, the general approach to every of these transmission schemes and standards. So yeah, that's a slide that is, yeah, it has a reference, it's the last slide, but practically this defines quadrature signals. I've looked at this at first and didn't really get it, so I designed another way to explain this, which is this Pac-Man figure. And it shows that there is an in-phase and a quadrature, which are the two components of a complex number. And you see that the tips of the mouth of this Pac-Man figure are actually the red dots, which are marked as e to the in-phase times 2 pi frequency times time. Practically, these dots work as shown with the arrows, so they move. And this is particularly used in every communication system, so this is a relatively central approach. And what we look at is the angle, which is 2 times pi times frequency times time, which should correspond to the frequency. So this Pac-Man particularly eats itself, so the red dots are rotating, depending on what is used here. This should symbolize the unity circle that is used to understand quadrature signals. You can also understand this as two laser cannons, which if you look at the right image, you see that it is E. At the E, there are these blue arrows, which practically symbolize the same. So you can look at code, which here is code for QPSK, which is quadrature phase shift keyring. That is used in IEEE 802.15.4, but there is no Q delay shown here. What this code is actually doing is at first it's an iteration within the infinite vector stream. That is because there's a ring buffer that is used to handle the vectors from the peripheral so that we have access to that kind of value set. And in the, under the loop, so that's the loop head, under the loop we see that there are two float variables defined, which is I phase and Q phase, which are the quadrature signals. And the rest is the sinus as a carrier, which we see here, and it's using square root 2 divided by 2 to actually modulate on top of the sinus, which is because if you use 4 points on top of the sinus pulse, and they are all in the same distance to each other, in the absolute distance, you get this square root 2 divided by 2, which is practically 0.707106678, which is just an approximation here. And if we look at this unity circle here, we see that practically QPSK modulates phase changes. So it modulates a change from 0 to 1, or from 1 to 1, from, this is not necessarily right in this slide, but it modulates the phase changes. And it uses 2 bits per symbol. And the phase angle changes by multiplications. So an interim summary here. All right, we have some DSP insights, and we necessarily need that thinking model to apply our code, to have code that actually makes sense to design a transmission scheme. We understand quadrature signals, which are practically used in every communication system. We understand that the radio peripheral and the device insights, which we gain, and the hardware requirement that there are define what we can do currently with our radio peripheral. So if it cannot receive the spectrum we are targeting, we cannot necessarily process any data with it. We have a terminology which is sample rate, down conversion, ADC, FPGA stuff. And we checked out some C++ to see why we use quadrature signals, which practically is a real implementation of QPSK. So at first, when I took the batch, or I had the batch at home, I wanted to define an FFT to look in the spectrum to decompose what kind of transmissions I'm receiving, but at the campsite this is practically impossible because there are very many batches. But I will try an FFT demo just to show this. I'm just Is it working now? All right, you see that the center frequency isn't defined as it should be. So I changed the center frequency as stated out at the demo. Just have to write down again. So what this actually does, it acts as a spectrum sensor for the communication of the mesh network that the batches are creating. Since there are too many batches here, I don't necessarily need to pull out my own batch, which I had to do at home to receive something at that spectrum. However, which we have to realize is that the batches are operating within the ISM band, which practically means that everything, be it Bluetooth or wireless LAN, can be in that spectrum. What I do is I hold a peak. That means I just take the highest point and lock it in order to realize that there is a pattern that is occurring in a certain set of frequencies. If you do this in a lab and it isn't actually showing too much here, you don't necessarily have that much communication in the wireless as we do have here. So a sufficient demonstration of an FFT just showing one peak for one batch or one set of frequencies is not necessarily possible, because I had to switch out all batches that are here or that at least are in the receivable area, which I did not do or which I cannot do. But normally you just get one of these peaks. So as I have shown, the FFT takes a peak and therefore defines where a target signal actually is within the spectrum. So within the ISM band, as I mentioned, there is a lot of stuff going on, so it's a little chaotic and disorganized. What we see to the right is a waterfall plot that practically logs over time what kind of peak occurred. So you see the green area to the left that marks that there was communication occurring at the frequency range from something around 2.47 gigahertz to 2.48, but there wasn't that much communication occurring from 2.482 to 2.492 gigahertz. So it practically shows that there's a diversion between the spectrums and it's practically a screenshot having a frequency range of 25 megahertz, which is the maximum you can do with the USRP2. And as I mentioned, you don't have a chance to really get a communication of the batch, since there are too many batches and you can operate on a definable set of channels, because at the batch, one channel is 1 megahertz, so you have very many channels and not necessarily know what you applied to your firmware at the batch, but practically you don't have that much communication or that undefined wireless spectrum. The problem of GNU Radio, at least for beginners or for most people who aren't necessarily working in telecommunication engineering, is that it has no documentation and no real introductory efforts. There is a developer documentation, but for somebody who wants to just work with GNU Radio, this is practically impossible to understand, because it uses a very specific terminology and tries to be as concise as possible. There is, as far as I'm concerned, no direct literature or no book that is just focusing the GNU Radio framework or an open approach. And there are very few presentations regarding on how to work with GNU Radio, since it requires to think in code, as I showed. It's C++ code, so it's not too easy to read in a presentation. And so many people use the graphical user interface to represent code, which I did too. But it just covers parts, so the functionality of GNU Radio that is within source is much more than what is shown in a GNU Radio companion. And yeah, GNU Radio is actually having lots of academic interest, and therefore there is much research, but that's not necessarily in software engineering. So we have telecommunication engineers who write software, but they don't necessarily write the software so that they can share the stack, or that they want to share the code. The architecture of GNU Radio is, as I mentioned, a language interoperability pattern. We have Python on top of Swig, on top of C++. So at C++ level, we simply process the vectors within the algorithms. But Python handled the connections, for example, from a modulation algorithm to a filter algorithm, or from a source to something like a filter, from a filter to a modulation, and from your modulation to a sink, and or to a source, very much depending on what you are modeling. But Python is not used for the digital signal processing algorithms. Python is also used for the user interface, which is practically rendering, as I have shown. The FFT is rendering the spectrum in real time, but that is on top of OpenGL, so that you have the adequate resources to visualize the spectrum, and that you don't necessarily need to render this in software. With the pointers, and I'm going to show this again in a later slide, but with the pointers you do a waveform transformation in C++. So you point into the vector stream, you have a for loop that iterates, and on this iteration of vectors you actually apply your algorithms. Swig is used as an interface generator for language interoperability, and yeah, the GNU Radio scheduler does the buffering. It's using a ring buffer architecture, so you don't necessarily have to do that. And since the framework is large and uses object-oriented programming a lot in C++ and many inheritance structures, practically you can use the framework and you can save very much effort. That comes to a price that you need specific software development know-how. So yeah, it's actually C++ inheritance, Python OOP with Qt and React stuff, which is used for the graphical things, and the real-time plots to leverage the GPU, so it's OpenGL programming sometimes. And I think, can you read that dark part, that readable? All right. So there are some parameters that are used to control the peripheral. These parameters, for example, are the center frequency, which is practically depending on the channel bandwidth. You can choose the center frequency and the decimation that is appropriate to your transmission scheme, so that you don't necessarily have to work with 25 megasamples for everything, which saves resources. these control parameters are applied here at the USRP, if I see this correctly, at the USRP source. So this is practically a receiver that is attached to an Ethernet port. And yeah, we see that there are some parameters shown in this table. The decimation is practically it's a constant that is used as a divisor for the 100 megasamples, which is corresponding to the 100 megahertz of the ADC operating frequency. And the Nyquist theorem applies, of course. If you're decimating by a constant that is too high, you may have aliasing effects. And yes, we have a gain that is, as I mentioned, for me it's just software, but you can have over-amplification so that you don't necessarily get any valid signal if you use too much gain. On top of that, as if this wouldn't be enough, you have a top block architecture which is defining a hierarchy. So if you're using a block, you can have, for example, stubs as sinks and sources, and later on attach different sources to encapsulate your packages, which may define transmission schemes that you have realized to analyze the certain set of wireless devices that you are targeting. All right, pretty much what that shows. This is a typical top block that is created with the GNU Radio Companion to receive a signal. This signal is at 2.405 megahertz. That's megahertz. And has no gain, so the source doesn't amplify the signal. And you have a sample rate of 25 megasamples, and you push this in a head, which just stops your receiver after 25 megasamples, so after 1 second. If you don't do this, your files grow large very fast, since the data rate is relatively high if you use 25 megasamples. The USRP2 source, it's actually, yeah, the FiSync saves the received signal as a C file, which corresponds to the complex values. So you each time have a pair of 2 4-byte floats, which is 32 bits, and it's single precision IEEE. I've mentioned that the blocks, and I'll show this later in a graphical representation, are created in XML. So what you see is that you define an XML scheme and put in your values, and you expose this file to the GNU Radio Companion. And afterwards, you have what is this showing? The QPSK modulation available in the GNU Radio Companion, and can use it for each transmission scheme you want to have it. And yeah, it shows that you have imports. So this is practically a Python import. Within the import tag, you have Python code, and the make is actually what is used to start the class. And if you use a QPSK modulator, you realize that you can use that modulator block in the middle, and you have a vector source that is feeding the modulator, and a Q-phase delay that is applied to do this modulation of QPSK into QPSK, which is then the Zigbee modulation. You can either pass this afterwards to a scope sync, which practically shows you a graphical scope, or you can pass this to a constellation to look that your modulation works properly. You can have different sources to debug your modulator, so if you see that it practically represents something you don't want to have, that you can therefore find your bugs visually. So this is a C++ code of a Q-phase delay. And what's of primary interest is the for loop in the middle that just shows that plus D delay is moving the in phase forward, so the Q-phase is therefore falling backwards automatically. The rest, as is GR complex, are again the pointers into the ring buffer, which are a specific GNU Radio data type that is introduced. And to the rest, you see that the template applies that is used to generate a signal processing block. So practically what you have to program if you're using the available templates within the framework is simply the for loop. And of course, the input and output pointers, but it's not too much effort for what it does. And since I mentioned that the GRC defines a code generation, it is putting this together as a Python script that is controlling the appropriate C++ classes that realize the signal processing. What I have done here is I have used a set of parameters. Well, parameters are named so that you can pass them with command line arguments and start your script and control it. And this parameter here defines the channel. And since IEEE 802.15.4 has, I think each channel is 5 megahertz. I think there are 11 or 12 channels, something like this. But at least, no, there are more channels, but it starts at 11 and goes to 26. So each channel corresponds to a frequency that is automatically set at the USRP2 sync. I've used an OFDM modulation, while OFDM is used here to do an interference simulation. And this OFDM modulation uses QPSK, which has an occupied tones, has 128 occupied tones, which generates an OFDM signal, or an OFDM QPSK signal of bandwidth of 4 megahertz. And since one IEEE 802.15.4 channel is 5 megahertz, it can actually disturb one entire channel. And with the parameters for gain, you can define the intensity of your interference. So with that, you can verify that your system that you are targeting does appropriate channel changes and therefore continues to work or fades to work. And since IEEE 802.15.4 is used for medical devices that have to cope with interference within the ISM band, this can be a relatively useful scheme to simulate interference in a laboratory environment. You see two signal sources that I used, one with a delay and with a multiplication. This is to pulse the signal so that you don't have a continuous interference, so that the interference occurs regularly and is therefore more effective and not triggering interrupt service routines at your controllers that you're targeting and DOSing them. You want just to simulate interference and not necessarily cause the devices to be irresponsive. So for an interim summary at this point, the GNU Radio Companion generates Python source code, which is relatively easy to manage since it is all graphical. And you can control the complete top blocks with scripts if you pass the arguments or the variables as parameters. And since Python doesn't know any types, it's relatively easy to do. We can use OFDM to spread interference over a range, which has been shown with QPSK and a bandwidth of 4 megahertz. And as I mentioned, this is useful to verify real-time capabilities on protocols like Zigbee, but it can also be used to, of course, to simulate interference with Bluetooth stuff. And since there are real-world use cases for this, this is relatively interesting and relatively cheap to realize. If you compare what kind of laboratory environment you would use without software-defined radio and peripherals and the approaches behind that. And you can use hierarchical blocks and that integrate themselves into the GNU Radio Companion after a restart. So everything you do is available afterwards. And therefore you can have a library and reuse everything you do. What we see here is an FFT again, but it shows that a device, which is the first leftmost arrow, is operating on a channel that is corresponding to 2.434 gigahertz. Sorry. And then there's interference that occurs, and the device changes the channel and stays operating within that channel and doesn't continue to work there. So the device reacts to the interference, does appropriate channel change. All right. And we have a restricted limit on instantaneous bandwidth. And that means we have 25 megahertz instantaneous bandwidth. And we can only monitor a limited amount of channels, therefore not the whole spectrum. Speed this up a little here. And yeah, the future of GNU Radio, since I mentioned there isn't too much user documentation, or I haven't come across any user documentation. I hope that there will be more graphical parts so that you can just click your stuff together and have a scheme for interference simulation or complete transmission and receive path. And yeah, GSE blocks, shared flow graphs, and I think what the radio currently is lacking is performance at the GUI things, because to be able to visualize your spectrum in real time, you need a comparatively fast machine. And I hope that there will be more capable peripheral radios that have more instantaneous bandwidth so that you can monitor more than just 5 channels and IEEE 802.15.4 or other protocols. For example, Bluetooth with its adaptive frequency changes scales across the whole ISM band, and you cannot monitor 100 megahertz with the USRP2. All right, this is particularly my last slide. So I've mentioned that this talk is named stuff we don't see every day, which is omnivorent like SmartDesk. But I think we can visualize this stuff with the approaches that have been shown, or with the radio itself and with the peripherals. And yeah, we got 1 inch deep. It's not too deep, I know, but we got 1 inch deep into digital signal processing. And I've shown some implementations of modulations and a delay that is used to change the modulation, and C++, Python, and XML, and yeah, some antennas on the radio peripheral design. Again, 1 inch deep. This wasn't supposed to be as deep as possible. And that should be pretty much it. I've used some sources, but particularly for the reference if you're interested, since the reference is relatively interesting to check out. So particularly, I'm finished.
So now we have about 10 minutes left for questions. If you have any, please ask them now. Yeah, please go to the friendly guy with the microphone.
I can hear you.
Okay. Every time we get to the new device, like sort of hard remote control or something, I always think, well, I wish I was smart enough to get into the new radio and the courthouse, actually to visualize what it sends out and like go to the vertical and everything. So my question is, if I wanted to build a device that can do that, right?
I don't understand anything you're saying. The echo is kind of passing in. You were asking for what kind of devices?
You were asking for, I'm sorry, you were asking what kind of devices used for the renderings?
No, if I want to take a device and transmit the ISM band, like a top for a car or something like that, and I want to see and visualize exactly what it's sending out and what frequency, and what's the protocol. What hardware do I need and what skills do I need?
To use GNU Radio, what skill do you need? Well, that's a question. I have really bad echo here. Can't really understand.
And also, which hardware do I need to be able to scan anything in the ISM band?
All right. Not necessarily no, but this the skill set that is needed to
Device that transmits the ISM band? Yeah.
Any device. So the complete range.
Yeah. So all the ISM band. So which hardware do I need? What skills do I need?
All right. Now I understood the question. I'm sorry. You can, of course, bundle a set of USRPs to cover the whole frequency range. So there are device drivers that act on IP or that work IP-based. So you can have 25 megahertz with the USRP2, and there are newer devices that can cover the whole ISM spectrum. To scan, I don't necessarily know what this refers to, but there is spectrum sensing. For that, or to understand that, I think a base in digital signal processing and telecommunications engineering is good. But I think a central skill is software development. And of course, Linux administration, since it refers to integrating with Hopper or interoperating with Hopper. I pretty much sense that covers it. I don't necessarily know, but we can talk later on if you want. Yeah. completely understand what is.
The GNU Radio looks very power hungry. I mean, you have a
Yes.
high frequency, a lot of digital logic.
Yeah.
It's also possible to use GNU Radio to optimize the power consumption of a final design of a radio. Or is power sacrificed for flexibility?
All right. GNU Radio mostly is used for rapid prototyping, so you don't necessarily optimize the power scheme of a real radio. But to the performance, it uses large I/O performance, so it's actually I/O hungry. It's not necessarily using much RAM or much CPU power. Yeah, I think in that case you could fall back to the traditional approaches, since GNU Radio is just to prototype transmission schematics and transceiver schematics.
No?
That's right. Questions to boss? I come down, it's completely impossible to understand anything here.
Are there any approaches to run audio codecs right with these features?
Of course, there are specific projects to check out audio codecs on Cgrand, which is the comparative repository for GNU Radio projects. You can check that out immediately, and there is code that interfaces with the GNU Radio framework, but not in graphical parts, so it's directly in code and not in the GNU Radio companion.
Okay, so I can run open codecs.
Of course, and vocoding stuff, you can have, yes, of course. I stay here, it's easier.
Hi. Welcome to Unity. I don't have actually a question or an addition to your answer about the hardware you need. If you have any questions about the hardware or you actually want to buy it, I bought a lot of numbers of things in Goldforce here, and at the end of CCC, they are for sale. So just come to the radio village, ask for Martin, it's me, and then I can show you what's there and our history to get some.
Absolutely, thank you.
Well, sorry, just lose the echo. Hard to understand if you're standing there. But everyone?
Okay. Anyone
All right.
more? Another one? Then please give a last applause to our nice speaker and